Welcome. Today I'm going to talk about learning objective 4, sequences, convergence. This is a core objective, which means it's important that you understand how to solve questions related to this because it will show up in future classes and it's one of the key objectives of the course. Um, Sequence convergence is useful in practice when you're deciding what's going to happen to a model of something in the real world, for example, in the long term. Oftentimes, you set up some sort of model and then you kind of let it run, like say a computer simulation or some game that you're playing, and um, you want to figure out what's going to happen at the end. So sequence convergence is like it's just asking what's happening at the end of a sequence of numbers. So it's much easier than figuring out what's happening at the end of a simulation. Ultimately, what's going to be the behavior. So we will especially focus here on three criteria. I can use calculus 1 techniques such as L'Hopital, squeeze, and theorem to find limits of sequences. Algebra is also super important in here. So I did a little bit of a review here on the side for this. So the main technique to remember from algebra is that you need to factor the leading term. So for example, let's consider a simple polynomial, 3n squared minus n. What's happening as n goes to infinity? We know this is a parabola, and because the coefficient here is positive, it's going to open up. And so in the limit, as n gets big, it should tend to infinity. Now, if you plug in infinity here, you would get infinity. 3n squared will be infinity minus infinity, and that's indeterminate form. So how could we argue using rules that indeed the limit is infinity here? And the key is to factor the leading term. So here we see an n squared and an n squared grows faster, so that's considered the leading term. And you can factor that. You could also factor 3n squared if you wanted, but it's easier to uh, just focus on the polynomial piece, the power, the n to n squared in here. So factoring n squared, we get this expression. And when you plug in infinity at this time, then you get infinity times 3 minus 1 over infinity. 1 over infinity tends to 0, so you get infinity times 3, which is infinity. So um, this makes sense. If you just had infinity minus infinity, that's an indeterminate that could have many solutions. So we couldn't just straight away argue that, although we can see here, hey, I know this infinity is going to be bigger than that infinity, but by how much? Is it 2 away? Is it, or is it infinity away from each other? So this makes the whole reasoning precise. Then another rule is L'Hopital's rule. And usually you use this in combination with some algebra. So for example, let's take this limit of 1 plus 1 over n to the n. This is famous because this is the definition of what E is. E is the limit, this limit, and then E is used for exponentials and natural logs. So it's important to know this limit. So how could we figure this out? Well, if I were to plug in infinity here, I get 1 plus 0 because 1 over infinity tends to 0 to the infinity. 1 to the infinity, you might say, hey, that's just equal to 1. Well, not quite, because this we're adding something to this infinity. Okay, so it might be a little bit bigger depending on this is tending to 1, but it's not exactly 1. 1 to any power is 1, but what if you're a little bit bigger? And so 1 to the infinity is an indeterminate. How do we solve this kind of indeterminate? We use rules of exponents and logs, exponentials and logs. So any number can be written as e to the ln of that number. So in this case, we consider this whole expression as a number. And so we write it as e ln to that number. Then the limit of continuous function just distributes in. So we can just look at the exponent here and find the limit of that. And that limit turns out to be 1, so that's why the answer is 1. But why is that limit equal to 1? This is where L'Hopital comes to the rescue here. First of all, the exponent here drops down by the rules of logarithms. Second, once we have it in this form, we have another indeterminate, infinity times 0, which we don't know what will it be equal to. It could be 0, it could be infinity, it could be something in between, and in this case it is actually 1. But why? So you rewrite this as a fraction to apply L'Hopital's. So we put this in the denominator, so you have 1 over n. And then looking at the top, the limit will be 0. The bottom will also tend to 0. So by L'Hopital, we get 1 over 1 plus 1 over n times the derivative of the inside, which is just negative 1 over n squared. So that's the derivative of 1 over n. And the bottom also is the same thing. The derivative of 1 over n is negative 1 over n squared, and so that quantity just cancels out, and we're left with 1 over 1 plus 0, which is 1. And so that's why this limit is e. And in fact, you should go ahead and graph this onto Desmos or some other graphing calculator and see indeed that there's a horizontal asymptote at e, y equals e for this function. Now this is certainly not trivial. And then squeeze theorem, if I had something with a sign or some oscillating quantity like negative 1 to n power, then I need the squeeze theorem. So sign is bounded between negative 1 and 1. And so we know that this quantity, whatever we're trying to find the limit of, is between negative 1 over n squared and 1 over n squared. Both of these tend to 0 as n goes to infinity. So by squeeze theorem, the middle function will also tend to 0, or the middle sequence in this case. So this is a quick review, but if you were confused on any of these steps, I highly encourage you to review this further. The second bullet here is that I can determine convergence or divergence of a sequence numerically and graphically. I like to use Desmos to graph sequences and see what's happening both numerically and graphically. And I'll show that in the sample question. And then lastly, given a bound epsilon for the difference between the terms of a convergence sequence and its limits, determine the minimal index that achieves that bound. This is useful when you're calculating something and you need it to a certain precision. Maybe you're taking the limit and you want to say, hey, I want to find a limit that's within 3 decimals of the correct answer. Then how do you know to get there? Well, that's what the epsilon is for. And so questions like this is like the first sample question here, where the epsilon is 0.02. And we're trying to find the minimal index n, so that for every n bigger than capital N, this is the case. So let's take a look at the first sample question here. We have n over n plus 1, and the first thing we want to do is look at the graph and the numerical pattern to see what should it equal. And I graphed this on Desmos already. So here we go. I put x over x plus 1, made a table, and looking at the graph, it's clear that it and the numbers here, it's clear that it's approaching 1. So I put a link here of that Desmos. You can go here to share and then copy the link and paste it in there. And so we can see there by the graph and table that the limit is 1. How do we argue using Calc-1 theorems and algebra? This we can just factor in the bottom the n and cancel. So then we're left with 1 over 1 plus 0, which is 1. And lastly, we need to do a little algebra to figure out this inequality involving absolute values. So after we find the common denominator, subtract the numerators here, we get absolute value of -1 over n plus 1. And n plus 1, n is always greater than or equal to 0, so n plus 1 will always be positive. The absolute value of -1 is 1, and 0.02 is the same as 1 over 50. Doing a little bit of rearrangement here, we get n is greater than 49, so capital N is 50. Notice here that n has to be an integer because we're finding the index of the sequence. That makes this true. So n greater than or equal to 50, and n being an integer, is equivalent to n being greater than 49 and n being an integer. Okay, thank you for watching. I hope this was useful. Have a nice day.